Hello, how's it going? So we're going to calculate surface area now. So imagine we have some surface in space. I'll call it S. And for now, we're going to think of this as some function of x and y, right? So we have the xy plane down here, right? So imagine this is the x-axis, this is the y-axis, and then there's a z-axis like that, right? So you have the domain down here somewhere, something like that, right? And the way we're going to do it is divide the surface up into tiny little pieces. So let's say this is one such piece, right? So it's a tiny surface patch. We can call it a patch, if you will. And it's just sitting above some rectangle in the xy plane, right? Right, and then we just add them all up, right? So the total surface area, so A for area, is just the sum of all those little surface patches here. So I'll call this delta S for now, and this is delta A, which is the area of the square, not necessarily the area of the patch above it, right? Right. So that's our goal, is to figure out the relationship between this delta S here and this delta A. Right. So let's essentially just take this and blow it up. Let's make it bigger so we can see. It might look something like this. Right. So this is our delta S. And right below it, we have our delta A. Right, and so we're going to imagine delta A as just delta x times delta y. Right. And so we can form the vectors at the corner here of the surface patch. Let's say that this is vector u in the x direction, and then say this is vector v in the y direction. And we're going to approximate the surface area, the delta S, as the area of this tangent plane here, right? Now, the way I drew it, it looks like the tangent plane, right, this area here it looks like a rectangle, but in general it's a parallelogram. And the delta S, they don't look like anything alike here, right? But remember, this is exaggerated. If you look at the picture up here, and I draw the tangent plane, you can see that there's not much difference, right? Because it's such a small piece, right? It's kind of exaggerated, the curvature of it, right? Right. Or put another way, right? If I make this even smaller, if I take like this piece of it down here, and then the corresponding piece of the surface, you can see that there's a slight difference, but it's much smaller, right? So yeah, that's kind of the idea, right? We're in the end, we're going to let all these deltas, go to 0, right? So delta S is approaching 0, right? Delta A is approaching 0, delta X is approaching 0, and so on, right? So in that limit, the parallelogram will very much be close enough to delta S, right? Okay. So how do we find the area of this parallelogram? So that goes all the way back to chapter 11. So the area of a parallelogram with the two adjacent sides as u and v is just going to be the magnitude of the cross product, u cross v. Okay? So what is that cross product, right? What is u cross v? Well, what is u, right? U is a vector just in the x and z direction, right? So here's the x direction. So it has a horizontal component in the x direction and a vertical component in the y direction, right? In the x direction, it's just delta x. That's a bracket. Nothing in the y direction. And then in the z direction, there's delta z. Right? So for the moment, we'll call it delta z. Sorry, I'm kind of at the edge of the screen here. Delta z. But delta z is very much related to the surface, right? If I draw this triangle down here, it might make it easier if I can draw it right. Right? It is a right triangle, right? So this is delta x, this is delta z. However, the slope in this direction, right, is just the partial derivative of f with respect to x. Remember what f is. F is just the function of the surface, right? So the slope in the x direction is just the usual partial derivative of f with respect to x, right? So, yeah, so this is essentially, approximately, right, delta z over delta x. So delta z, in this context here, this delta z is really just the x partial of f times delta x. Okay, so I know that's very small, so let me rewrite that up here. U, the vector u, has three components. The components are delta x, 0, and the x partial of f times delta x. Okay, and then we can do the same thing with the vector v. Right, so here's the vector v. It has two components. I'll go up here. Right, so the triangle is in this direction now. You have your delta y, and then your delta z. It's a different delta z here, right? Here delta z will be the y partial times delta y. So your vector v will have three components, 0, delta y, and fy delta y. Again, I'll write it bigger in just a second, right? But is that clear that the slope here is the partial of f with respect to y, because you're now in the y direction? So v, as a vector, is going to have component 0, delta y, and the y partial of f times delta y. Okay, so now we can take the cross product, u cross v. So let's do it this way, right? You use the determinant again, I, j, and k for the top row, and then u1, u2, u3, and v1, v2, v3, right? And then, yeah, just substitute. These are the three components here, right? Okay, so the I components, right, will have determinant u2, v3 minus u3, v2. So that's going to be, well, 0, and then minus fx, delta y, delta x, right? And then for the j component, we'll have v1, u3, which is 0, and then minus fy, so the y partial of f, times delta x times delta y. And then the k component will just be delta x times delta y minus 0. Right? So, yeah, as a vector, it's just these components. Oh, and we can factor out the delta x, delta y. Yeah, So that's the cross product, but remember the area is a number, it's not a vector, right? So we need to take the norm or magnitude of that vector. Right? Again, the delta x, delta y is a common factor, so that can just come outside. And now it's just going to be the partial of f squared, right, plus the partial of y squared, right? We're squaring a negative, so it's positive, right, plus 1 times delta x, delta y. And I'll put the 1 in front, although it doesn't matter. Right. So there you go, right? There's the area of this parallelogram, and that's going to be, so this is the area of parallelogram, which is approximately delta s. Sorry, not delta A, delta s, right? So we're approximating that the area of this delta s, this surface patch here, right? Yeah. Again, maybe not a very good approximation, but as delta s gets smaller and smaller, right? See that they're gonna line up pretty well, right? So. Right, so yeah, so now we just take the limit, right, as delta s approaches 0. Remember, we call that ds, and our delta x, delta y is your dx, dy, which we can just call dA at this point. Right, so ds is going to be 1 plus the partial of f with respect to x as a function of x and y, right? It will depend on where we are in the xy plane, right, squared, right, square the whole thing, plus the y partial squared, right, times dA. Okay. Yeah, so now we just add them all up, right? And, you know, when they're little rectangles or patches, you're just taking a finite sum, but in the limit, right, the sum becomes an integral, right, in the limit. Sorry, can't spell limit. As delta A goes to 0, right, which means, you know, dA at this point. Yeah, so the total area then, right, which again, I'll just call A for area. It's going to be the double integral over the surface, because it's a two-dimensional surface, of ds. Or, as a practical matter, right, the delta s, or the surface S, is over some region R of the xy plane. Right? Essentially, that's the domain, the x's and y's, right? So over that region, we're just going to calculate this double integral. And I think I forgot something important here. This is the magnitude squared, right? I forgot to take the square root. So it's to the power 1/2. And maybe just to make that clear, this is the square root of this. Yeah. Yeah, so it's not the magnitude squared. It's supposed to be just the magnitude itself. Yeah, so I forgot the square root. And yeah, here as well. So square root of 1 plus fx squared plus fy squared. Okay, all right, now I think it's right. Yeah, okay. So that's essentially the formula for the area of a surface. And let me just rewrite it one last time, right? So the area of a surface S, surface S, is going to be the double integral over the region R of the square root of 1 plus, again, partial of f with respect to x squared plus partial of f with respect to y squared. Take the square root of all that. And then dA, of course, could be, dx dy, dy dx, right, depending on if it's vertically simple or horizontally simple. Or it could even be, r dr d theta if you want to use polar coordinates. Right. So, yeah, again, if you take away anything here, right, this is the formula for surface area. It's on your formula sheet, so it's not like you have to memorize it or anything. But this is what we're going to use as a practical matter to calculate surface areas. And just like with arc length, right, because of this square root, this is not something that is usually easily integrable, in the sense that you're not going to get, nice functions here. So in many cases, you're just going to have to do this numerically, plug it into a computer or a calculator to get to do the integrals. So the few examples that there are in the homework are usually ones that you can actually evaluate. But in many cases, you may not be able to evaluate it, by hand. So just plug it into a calculator, computer, and it'll spit out the approximate answer. And, for those purposes, an approximate answer will be good enough. Okay, so our examples here will be a little contrived, right, in the sense that they'll be very simple. They'll be, right. It'll be in such a way that we can evaluate this double integral, this iterated integral here. Okay, so here's our first example. We want to find the surface area of the portion of the plane, so the part of the plane x plus 4y minus z equals -5, over the rectangle R, and, well, maybe we should just graph that rectangle. So x goes from 0 to 2, and y goes 1, 2, 3, 4, 5, a little bit exaggerated, but right. So this is our R, this is our rectangle. But again, we're not finding the area of that rectangle. What we're finding the area of is the following. Right, so there's a plane, and I'll try to graph the plane. So yeah, when x and y are 0, z is going to be 5 already. And yeah, it's going to look something like this, right? At least that's the portion of it sitting above the rectangle here, right? So the green rectangle is in the xy plane, right? 1, 2, 1, 2, 3, 4, 5. So that's my R. And so we're looking for essentially the area of this portion of the plane. So yeah, just this piece of the plane right here. Okay. So yeah, what's the area of that? Well, we have a formula for that, right? Let's just compute the double integral. I'll just copy down the formula here. The double integral over the region R of the square root of 1 plus fx squared plus fy squared dA. And because this is a rectangle, we can use dx dy, in other words, treat it as horizontally simple, or we can treat it as vertically simple, right, and do dy dx. Yeah, let's do that, right? I kind of like that better in most cases, right? But what else do we need here? We need fx and fy. We need the partial derivatives. So the real question is, what is f, right? Remember, this is the surface, right? Z as a function of x and y. And they give us the plane in standard form, right? But we want to solve for z. So z is going to be x plus 4y plus 5, right? So I just solved this for z here. And now I just take the two partial derivatives, the partial of z with respect to x, or better yet, fx, as a function of x and y. Yeah, that's just 1, right? It's just a number 1. And then with respect to y, that's just a number 4. So, yep. Right? So we're just calculating the integral of the square root of 1 plus 1 squared plus 4 squared. And then this will be dy dx. Okay? Now, what are the limits, right? What is y doing? Well, it's right here in the region. Y is going from 0 to 5. Right? And what is x doing? X is going from 0 to 2. Right? So yeah, when it's a rectangle, it's very easy to get the limits, right? If it's a more complicated region, if y is some function of x here, then, then that becomes your upper limit for y. It could be a function of x, right? Just not in this case. Okay, so this integral here could not be any easier. In fact, you're probably way ahead of me, right? 1 plus 1 plus 16, right, is 18. So we're integrating the square root of 18, right, over this region R. And the square root of 18 is a constant, so we can take it outside. And now it's just a formality to do these two integrals. After all, this integral here at this point is just the area of the rectangle, which of course is just 2 times 5. So this integral here should just be 10 times the square root of 18. Right? Yeah, obviously you can work them out, but when you integrate y, you just get y evaluated between 0 and 5. And then you do the integral here. So this is just the integral of 5. So when you integrate that, you get 5x. Plug in the 2 and the 0. You get 5 times 2 minus 5 times 0, which of course is the 10. So yeah, so that, you can work it out. It's just a few lines of calculations. But I'm basically treating this as the area of the rectangle, the area of the region R. Right, R for region or rectangle, at least in this example here. Anyway, so we have our answer, right? The surface area, A, is just the square root of 18 times 10. But we can simplify that, right? 18 is, after all, 9 times 2, and the square root of 9 is 3. So 10 times 3 is 30. 30 times the square root of 2. Right? So that's the exact area. And if we want an approximate area, just use your calculator. I think it's 42.43. Okay, so yeah, again, a very simple example, and one where the integral is obviously very easy. Should be easy at this point, right? But like I say, this is more the exception than the rule. Most of these integrals here, this integrand here, will be complicated enough where trying to do the, even the first integral here, the first definite integral, might be problematic, to say the least, right? Or just impossible to do exactly, right? So that's why we have calculators and computers, right? Okay, so we'll do another example. Find the surface area of the function. So this is z, right, as a function of x and y. And it's just y squared. So you know what that is, I hope. Over the square r. So here it's not even, it's a rectangle, of course, but it's since the sides are equal, they're just 3 each, it's a square. So that's the region over which we're integrating. Right. So if you want to graph the function, this is z. And this is, I'll make this the x-axis and this the y-axis, right? So, oh, I think I got it backwards, right? Z is equal to y squared. All right. So here's the z-axis, approximately. Here's the y-axis. And then here's the x-axis coming out at us. Yeah, if you graph this surface here, this is a cylinder, right? It's a parabolic cylinder. So here's the parabola, right? This is just z equals y squared in the yz plane, but it doesn't depend on x, right? So it's just this cylinder here. Oops. I think I got that a little bit wrong. They're not exactly parallel here, but right, so you get the idea, right? This is a parabolic cylinder, and again, we're only taking the portion of it that's over this square here, right, where x and y are 3, right? So effectively, it's just this portion of the cylinder. Again, maybe a bad orientation of it, but so if I do it this way here, yeah, it's this patch of it, this being the x-axis now, and this being the y-axis, right? I think, yeah. Okay, so what is the area of that part of the cylinder, parabolic cylinder? Okay, well, we just do the integral here. Here it is again. D8. Right, and yeah, so since this is a square, you're just integrating from 0 to 3, 0 to 3, and then fx, of course, is 0, fy is 2y, right? Oh, yeah, right, so don't forget you have to square that, right? So this is just 1 plus 4y squared. And then we can do dx dy or dy dx, it doesn't matter. Yeah, let's do dx dy. It really doesn't matter here. Because this is a function of y that can come outside. Right? In other words, you can split this up as the product of these two integrals, these two definite integrals. Again, don't make the mistake of doing that always, right? This is a special case where this does work. But usually it doesn't, especially when this 3 here might be a function of y or a function of x. Right? So, yeah. Oh. Okay, so the first integral, of course, is just 3 here. But it's the second integral that might take a little bit of work, right? So it's going to be 3 times this definite integral, 4y squared, right? Yeah. And so this is not a trivial integral. This is not one that, you know, it's not basic substitution, right? So it's not u is equal to 1 plus 4y squared, right? Because there's no y on the outside of that, right? All right, so let's see. How can we evaluate that in just a few lines? Now, I'm pretty sure it's a trig substitution. At least that's how I would do it. There might be other ways, but so this is a good review of Calc 2, trig substitution, trig sub. And I would start with just drawing the triangle here. It doesn't have to be to scale. So here's our angle, here's our right angle. And this looks like the hypotenuse, right? This looks like this, right, square root of 1 plus 4y squared. And now it's just a matter of what's the 1 and what's the 2y. So I'll make that the 1 and that the 2y, I think. Right. So, well, maybe I want it the other way. Maybe I want this the 2y and this the 1. So yeah, sine will be 1 over the square root of that. So that'll be cosecant. Oh, I'd rather have secant. I changed my mind yet again. Okay, so cosine of theta, right, is 1 over the square root, which means secant of theta is the square root of 1 plus 4y squared, right? And so, yeah, we're integrating secant of theta here. However, what's y, right? So 2 times tangent of theta is 2 times y over 1, right? And so y is just 1/2 tangent theta. And so dy is going to be 1/2 secant squared of theta, d theta, right? So let's see, the 3 comes from the dx integral. And now we're integrating the square root of 1 plus 4y squared. That's just secant of theta. And the dy is 1/2 secant squared of theta, d theta. And theta is doing what? Well, let's see. If y is 0, then that's tangent of something equals 0. Tangent of 0 is 0, so that's still 0, right? And if y is equal to 3, that means that tangent of theta is equal to 6. So theta is just the arctangent of 6. Did I get that right? So yeah, if y is 3, yeah, arctangent of 6. All right. So the 1/2 we can pull out. So this is 3 over 2. The integral from 0 to arctan of 6, whatever that is. And then secant times secant squared, of course, is secant cubed. Which, of course, is also not quite a trivial integral here. Okay, so secant cubed. Well, it could either be a reduction formula, which I certainly don't know by heart. I'd have to look it up. But the first thing that came to my mind, and I'm still dreading it, I don't think this will be necessarily easy here, but so I'm just going to call this, I don't know what to call it, just A for angle. So A is arctangent of 6. So yeah, the first thing that came to my mind was split it up as secant theta and secant squared of theta. And if this is the derivative of tangent, right? Tangent is the derivative of tangent is secant squared. This would be my u. So this looks like integration by parts to me. So we remember integration by parts, I hope. uv minus the integral of v du. Yep. So yeah, so the integral of, well, so u is secant, and dv is secant squared, which means v is tangent. And du, the derivative of secant, is secant times tangent. Right. So let's see how this works, right? So u times v is just secant times tangent. And we'll plug in the 0 and the a later. Minus the integral of v du. So that's going to be tangent times tangent. So tangent squared times secant. Again, from 0 to a. So let's see, if u is tangent, the derivative of tangent is secant squared. We don't have that. Or what we could do, let's plug in the a here, right? Secant of a tangent of A, and then tangent of 0 is 0, secant of 0 I think is, oh, well, it doesn't matter. Secant of 0 is 1, but 1 times 0 is 0, so when you plug in 0, you just get 0. All right, so minus the 3 over 2 gets distributed, right? Yeah, I guess we're going to think of this as secant times tangent times tangents. Is that right? So secant, yeah, I don't see how that helps. Oh, tangent squared is 1 plus tangent squared is secant squared, right? So this is going to be secant squared minus 1. Oops. Secant squared theta minus 1 times secant theta d theta. There we go. Yeah, so we get all this again. And then we're going to get secant cubed, which I know is what we're looking for in the first place. Let's split this apart, because you can see where this is going, I hope. Theta d theta. Right. So originally this was the integral of secant cubed. So yeah. And then the integral of secant, hopefully you remember that. I think I remember it. It's the natural log of secant plus tangent. Right. And you can do that by multiplying top and bottom by secant plus tangents. Okay, so at least I remember that. All right, so this is 3 over 2, right? Secant A, tangent A, and then let's put the minus 3 over 2. So natural log of secant of A plus tangent of A, and if you do the natural log of secant of 0 plus tangent of 0, 0 instead of theta, you just get the natural log of 1, which is 0, right? Okay. Minus 3 over 2, the integral from 0 to a of secant cubed, which is what we're looking for. And of course, this whole thing was equal to 3 over 2 times the integral from 0 to a of secant cubed. Theta, right? So we'll just add this to both sides. Right, and so we'll get 3 on the right. Okay, so let's switch sides. I'll put it on the left. And then on the right, we get the 3 over 2 times secant A tangent A minus 3 over 2 natural log of, I assume this is all positive here, secant of A plus tangent of A. And we could have pulled out the 3 over 2 here. So that becomes 2 times this integral, secant cubed, is equal to secant of A. Well, we'll have to figure that out in a second here. Tangent of A minus the natural log of secant of A plus tangent of A. Right, so then just divide by 2 here. So 1/2 here, 1/2 here. All right. Finally, what is the tangent of A? Well, remember what A was. Arctangent of 6. So the tangent of the arctangent of 6 should be 6. After all, A was defined to be the arctangent of 6. And now we need secant of A. So another triangle, 6 over 1, that's your A. And so this is going to be the square root of 37. Is that right? Yep. In which case, secant of A is 1 over cosine, so I think it's just square root of 37. Yep, so secant of A is the square root of 37. Okay, now I think we got it. So the integral from 0 to, again, arctan of 6 of secant cubed is 1/2 square root of 37, and then tangent of A was 6, right? Minus 1/2 natural log of square root of 37 plus 6. So 3 square root of 37 minus, and I think I'll just leave this alone, 1/2 the natural log of 6 plus square root of 37. Phew. Yeah, I think, so if you didn't believe me when I said that these integrals are not altogether that simple, yeah, no, they're not. Let me make sure. I had the 3 here. I kept the 3. So I think that's the area. It's the exact area. We can approximate it. I get about 17. 17.0024, which I guess is a reasonable answer. It's hard to tell. Okay. Yeah, sorry, this is not right. Because I just checked. I plugged it into Wolfram Alpha, and it gave me the answer of 29.2413. Well, so much could have gone wrong here, and it might take me forever to figure it out, but let's see. So I think the 3 is correct. The integral here is correct. Secant squared, integration by parts, and then minus 3 over 2 times the integral, secant squared minus secant, or secant cubed minus oh, there we go, plus. See, you're subtracting a negative, oops. Okay, so I'm you know, I hope most of you figured that out, that this should be a plus here, right? Or rather, without the brackets, it should be a plus. Yes. Right, so this should be a plus. Right, and then I switch sides. So yeah, okay, oh, very easy fix here. It's plus, not minus. Okay. All right, so now, if we do the same thing but with a plus. It's still wrong. So now I'm getting 19 point, I just had it, 4942. Sorry, 19.492. Well, okay, maybe I should just leave it and come back to it later. So, so I checked. Oh, yes, the integral of secant, right, from 0 to a is 19.4942. Right, but the surface area is this, so I forgot to multiply by the 3 over 2. See, the 3 over 2 ended up getting canceled here, right? so there should be a 3 over 2 here that wasn't supposed to be there in the first place. So yep, now when you multiply by 3 over 2, now it's correct. So 1.5 times 19.4942 is the correct answer, right? Oh, yeah, so this is correct here, this. And then when you multiply by the 3 over 2, you do get 29.2413. Okay, so that's the actual answer. And it's confirmed by Wolfram Alpha, or at least that helped me figure out where I made my mistakes. All right, well, there you go. Not an easy problem by any stretch, but it was doable. I mean, we got not only the approximate answer, we did get the exact answer here, and maybe for posterity, we should write this down. So the surface area is this answer here, which is just the integral of secant cubed multiplied by 3 over 2. So we get 9 over 2 times the square root of 37 plus 3 over 4 times the natural log of 6 plus the square root of 37. And one last calculation shows that this should be, 2413. Right, so the point of that is that, we have the exact answer and we have the approximate answer. And very unpleasant to get the exact answer, or the approximate in this case. I forgot the one here, 29.2413, yeah. Okay, but my point is that, hey, we got the exact answer. It's a pain, but it's doable. On the other hand, there are many problems for which you're just not going to be able to get the exact answer. In that case, just get the approximate answer. 4 decimal places is perfectly good enough. All right. So that's a surface area problem. We'll do another one. All right, so the question is to write an iterated integral for the surface area of the function f of xy equals e to the xy over the triangle with vertices 0, 0, 1, 0, 1, 2. So that's not hard. All right, so here's 0, 0, 1, 0, 1, 2. Okay, so it's not a rectangle anymore, it's a triangle. Okay. And so, we can describe this region R as the set of points x, y, such that x is between 0 and 1, and y is between y equals 0 and y is equal to 2x, because that's the line with slope 2 here. Right? Yep. And x goes from 0 to 1. Okay. Right, so now to get the area, we integrate over R the square root of 1 plus fx squared plus fy squared dA. And in this case, R, we'll do this vertically simple, because that's the way I wrote this. It's for a vertically simple region. You could, of course, do a horizontally simple region. It's not that bad. So y goes from 0 to 2x, and x goes from 0 to 1. So dy dx. And we also need the partial derivatives, right? So if f is just, f of xy is e to the xy, the x partial is y e to the xy, and the y partial is x e to the xy. So, when you square it, when you square them, you get y squared e to the 2xy, and then for fy squared, you get x squared e to the 2xy. So our integrand here will be 1 plus y squared e to the 2xy plus x squared e to the 2xy. And of course we can factor out the e to the 2xy. So 1 plus e to the 2xy times x squared plus y squared dy dx. Okay, and there's our iterated integral. That's all, right? That's the question. Write down the integrated integral, right? And on a test, I will be very clear. I will say, do not evaluate, because obviously that's the hard part, right? Yeah, I mean, for problems like this, writing down the integral is all we need. There are computers that'll approximate this, and let's see what they say. Okay, so Wolfram Alpha says this is 2.56775. Right, so it's an area, square units. Yeah, so there you go, right? There's no point in trying to do this by hand. To be honest, I would have no idea how to do this by hand. Because I see x squared plus y squared, I'm tempted to think that this is, polar coordinates. But, that's, it's not trivial, of course, because this is not a polar region. So we'd have to get the region now would be very difficult, right? If the region were, a circle or a semicircle or a quarter circle, that would be reasonable. But because the region is not, symmetric, radially symmetric, I wouldn't think switching to polar coordinates would necessarily make this a whole lot easier. So luckily we don't have to worry about that here. We don't have to try to evaluate it. Why did I do it in the last problem? Well, mostly as a review of Calc 2, right? Make sure you know your integration by parts. Make sure you know your trig substitution. In that case, we kind of had to do both. And maybe there was a way to do it, using just one and not the other. I don't know. So anyway, it's a good review. But this one, I think, even for Calc 2, would be pretty insanely difficult, if not impossible. So we're going to be happy with an approximate answer here. Okay, one final example. They give us the function f of x, y is the square root of a squared minus x squared minus y squared. You should know what that is, right? And we want to evaluate this surface integral here. Right. Remember, the first thing we do is we write this as the double integral over the region R of 1 plus fx squared plus fy squared. We'll take the partial derivatives in just a minute. But what is the region R here? Right. So for that matter, what is the surface? So I think we'll just graph the surface here. Right, so remember, this is z is equal to the square root of a squared minus x squared minus y squared. You square both sides. And then add the x squared plus y squared to both sides. Right, so this is a sphere of radius a, centered at the origin. But remember, it's only the plus square root, so it's only the top half of the sphere. So top half of the sphere, or if you prefer, spherical dome. So let's say this is A here, this is A, negative A, negative A. The region R is just a circle. And then the surface, of course, is the dome, the semi-spherical dome sitting above it, right? Yeah. Okay, so yeah, we're looking for, this is our surface S, and we just want to do the double integral, so we want to find the surface area of this spherical dome. All right, So I already wrote down the integral, right? We know what r is. Well, it's right. It's just this disk here. So r is the disk, set of points x, y, such that x squared plus y squared is less than or equal to a squared, right? Oops, that's a bracket. So yeah, disk of radius a, closed disk of radius a. Right. So now let's do the partial derivatives, right? So f is a squared minus x squared minus y squared to the 1/2. So the partial with respect to x is going to be, let's see, negative x over the square root of a squared minus x squared minus y squared. And then the y partial will be negative y over the square root of a squared minus x squared minus y squared, if I did that right. Don't forget we have to square them. So fx squared will just be x squared over a squared minus x squared minus y squared. And fy squared will be y squared over a squared minus x squared minus y squared. So this combination here, right, this square root, if I take 1 plus fx squared plus fy squared, again, I can't forget to take the square root like I did already, you're going to get 1 plus x squared over a squared minus x squared minus y squared plus y squared over a squared minus x squared minus y squared. Right, again, don't forget to take the square root. So this is looking pretty bad here, right? This looks like this is going to be a very difficult integral to do, you know, compared to the last one, probably almost as bad, right? Well, this is where a little bit of algebra will help. If we get a common denominator here, we're going to get a squared minus x squared minus y squared, right, over itself, right, because that's the 1. 1 is, right, a squared minus x squared minus y squared divided by itself. That's a y, sorry, I keep messing that up here. And then plus x squared plus y squared. So, yep, in the end, you see what happens. Negative x squared plus x squared is 0. Negative y squared plus y squared is 0. So the numerator is really just a squared. And when you take the square root, you just get a. So this is the integrand here, right? This is the square root of 1 plus fx squared plus fy squared, right? So that's all we're integrating. So now we can write the area as the double integral over the region R of a divided by the square root of a squared minus x squared minus y squared dA. And because this is a circular region, I would think that the region R is really just the set of polar coordinates such that R is less than or equal to A, right? Yeah, it's a circle. It's a disk of radius A, right? So yeah, if it's all the same to you, R goes from 0 to, well, let's say theta goes from 0 to 2 pi, and R goes from 0 to A. And so this is going to be A divided by the square root of A squared minus R squared. Okay. And of course you might be thinking, well, that's not an easy integral. That's probably going to be a trig substitution. Or you could look up the formula. But it's actually easier than that. It's Calc 1. Don't forget the R here, right? Remember, dA is R dr d theta. So this really is just an ordinary substitution here, right? This is just u is equal to a squared minus r squared, because du is negative 2r dr. So we'll multiply by negative 2 and divide by negative 2. Right, so yep, we get negative 1/2, the integral from 0 to 2 pi, d theta, nothing depends on theta here, and then 0 to a. Oh, we can take the a out. A is a constant, right? Yeah, let's clear that. Right, so a is the radius, a is the constant, right? So we're going from 0 to a. of 1 over the square root of a squared minus r squared. And again, we have negative 2r dr here. So negative a over 2 times 2 pi, that's the integral from 0 to 2 pi. All right, and now when we do the substitution, what are we going to get? We're going to get du over the square root of u, or as I would prefer, u to the negative 1/2 du. So, right, if r is 0, right, u is going to be a squared. And if r is a, u is going to be 0. So we're going from a squared to 0 now. So if you're worried about getting, sorry about that. If you're worried about getting the negative here, yeah, when we switch, we'll get a positive, right? So far we have what? We have negative, the 2's cancel, pi times a, and then the integral from a squared to 0 of u to the negative 1/2. But if we make that a positive, we're going from 0 to a squared. And then when you integrate, you just get 2 times the square root of u. A squared, sorry. And the square root of a squared is just absolute value of a, but a is the radius, a is positive. So pi times a times 2 times a, or 2 pi a squared. And that's the area of this surface. Right? So this surface has area 2 pi a squared, which is no surprise. Remember, this is half of a sphere. Right? If you want the entire sphere, top and bottom half, the area is 4 pi r squared. But we just got the top half, so half of that area is 2 pi r squared. Oh, right, we're using a for the radius here. Right, why don't we use r? Well, because r is the square root of x squared plus y squared. R is a variable, so we don't want to use r. Sometimes I use capital R for the radius as a number, but capital R can also mean the region. However, in the context of a limit, we know that here r represents a number. Here r just represents the symbol for the region. So usually there's no confusion there in most cases. But there it is, right? Here they wanted the radius to be a instead of capital R. All right, yeah, so that just confirms that the surface area of a sphere is 4 pi r squared. No surprise, we knew that all along. But this is one way to figure that formula out. And there, I'm struggling to remember, but I know there's a pretty good video. I think it's 3 blue, 1 brown, that gives you this intuitive idea of where this 4 comes from. After all, pi r squared is the area of a disk, right, of radius a, and so the idea is you should be able to cover this sphere with 4 disks of the same radius, right? And again, that doesn't look obvious, right? It looks like we can cover the top maybe with this, and then the bottom, and then how can I get the other 2? You kind of have to cut them up, right? But I think if you just Google, area of a sphere, or surface area of a sphere, and then 3 blue, 1 brown, I think there's a pretty good video that will talk about that. I'll post it in the link if I can find it. Post it as a link in the description, sorry, if I can find the video. Anyways, for our purposes, you're just doing double integrals for surface area. And in some cases, you don't have to evaluate, right? Do not evaluate. And in other cases like this, it's a little bit of a hassle to evaluate it, but it's not beyond reasonable here. This is a very reasonable type of problem, this example 4. I would go back to example 2 and say it's, not reasonable to work that out by hand, but I did it, And you should know how to do that by now. And it's good practice. It's good, review from Calc 2. All right, so that's surface area.